Now, since you guys have been into the project for about 2 weeks, now is the time to talk about ETF because you have struggled through it. So now I just want to talk about some big picture about why we are doing ETF to give you some idea. And then I'll move on to a new topic. Okay? But you should see the Oracle, right, from last night. You should really check the Oracle thoroughly. If you find any issues about the Oracle, please let me know. I will fix it. Okay? Okay. I just want to talk a little bit more about ETF, not really from the Eiffel perspective. It's actually quite a nice framework which you can also try to build later on when you do your own projects. Okay? Basically, we are trying to talk about how you can do acceptance tests. So the acceptance test over here is kind of different from what we did for unit test. For example, the JUnit test which we did in 2030, or the e-spec test that we did up to now. So it's a little bit different. Okay? So now let's again try to see a very simple example. Let's say the one you read from the tutorial documents. Let's say we are trying to build a system, build a software for a system for bank ATM machine. Okay, so here are simply just 2 examples here. We simply got the so-called concrete user interfaces. When I say concrete, I mean you already got hardware there built up for you for the user interface. You got the button click, you also got confirm or keypad, etc. They are concrete. But we want to show that when you are trying to build up the system, it is not so necessary for you to get a concrete interface first before you can build up your system. You can always try to prototype your system before you try to commit to the concrete one later. Okay, let's just see. Again, we got separation of concern. Separation of concern is always a good principle for you to follow. You want to do one thing and do it well, like the Unix principle, right? Each command does only one thing and does it well. Okay? So now, first of all, let's talk about the concrete user interface. So what options do we have? So for the concrete user interface, when you have the executable for your project or for whatever programming language you're building, once you get the executable, all the classes, methods, features, or functions, they are basically hidden. So the users just cannot see them. That's why you need the interface to actually interact with. Now, you got many options there. It can be web, like what you learned from 1012. It can be mobile app, like what you learned from 1022. And also, you got desktop application as well. Okay, so these are the concrete ones, but they take time. They take time to really develop, which means you really don't want to distract your attention to develop your user interface. You want to focus fully on business model. Okay, that's why another concern is really about the business model. For example, let's say for your projects, you're trying to build a static analyzer for some expression language. In this case, the project would be much tougher. If I say, apart from building the analyzer, the model classes, I want you to support also some web application or mobile app, like what you did in 1022. In that case, you're going to spend another maybe 10 or even 100 hours to tailor the GUI, the user interface. But that's not the point. We really want you to focus on the business model. That's really the logic. So once you got, the idea is, once you get the logic right, it doesn't matter what kind of user interface you're trying to connect that into. Okay? User interface is second issue. Okay? Okay, you implement the classes and features depending on what language you're talking about. It does not have to be Eiffel. It can be Java, it can be C++. So these are the core logic. Okay? So now exactly how the bank stores, processes, and retrieve information, in the various way. Now, what about in practice? So here you can see we got 2 concerns. We got the user interface you want to support. That's definitely important. But do we really have to prioritize that over the business model? The answer is no. That's something we want to teach you for the projects. You want to prototype something quickly before you get to the user interface to commit. Okay, so you want to test your software as if you were a real app as soon as possible, way before you try to build up the concrete user interface, before you ever try to deploy that on a maybe Android tablets or web browser. Okay, so now what's really important here, you can see maybe that's something you have noticed already in ETF projects that we gave to you. The model cluster somehow is independent of everything else. So everything else somehow just works for you. So you just have to focus on designing your implementation for analyzer. Once you're done with it, you can somehow just connect them to the rest of the world in a very easy way. I will just give you some idea, okay, at the end. Okay, how do you prototype system with abstract UI? Okay, let me just see. Okay, so that's ETF. That's one way for you to do it, just in Eiffel. Of course, you can try to find out the similar framework for other languages. They should have something like this, okay? Which means you don't necessarily have to build up the concrete user interface right away. You can just prototype it, okay? Okay, business model. Okay, now I want to just clarify some concept over here, okay? So whenever we talk about interaction of the user with the system, we want to distinguish between events and features. So events are the high-level user-concentrated, user-centric phenomenon that you want to concentrate on. Features are programming artifacts, like methods, functions, whichever language you are programming in. Okay? I just want to clarify that. Now I want you to also draw the link to lab number 4, when you did undo-redo lab, right? In that case, remember in lab number 2, what you did in lab number 2 was to program the business logic, the game for PEG solitaire. And then in lab number 4, we try to introduce another layer of user interface with the command pattern, okay? So each command is simply the abstract way of telling how the user is going to interact with the system. The user may want to say, let me just draw some diagram here to show you. Okay? And you apply the same idea for the project as well. Okay, let me just draw this very quickly. So now let's say the user over here, they say, I want to move left on a particular slot, for example, 2 and 3. In this case, in your system, there are 2 separate clusters. One is called the user interface, okay? And also you got another one, in this case, let me just call it game. But at the same time, it's also the model. The user does not interact with the game or model cluster directly. That's not what you do. What you do is you got different classes of command. You got command as a superclass at the top, and then you got various different commands. For example, move left, and also move right, and etc. Okay? So now let's say the user try to initiate this command over here. What it does is it's going to instantiates a command object. In this case, it's going to do the move left command. And then the move left command is somehow connected to some global shared instance of the game, right? In this case, it's going to somehow make some call to the model. In this case, that'll be the game. Okay? So that's our solitaire game. The same pattern also apply to the projects. Now, I can just basically replace almost everything with something very similar. Okay? Now, let's say that in the projects, how is this similar? For the projects, the user might say, now I want to do type check, for example. Okay? I'll just give you a different example in the same framework, the same idea. Now, in the case of the static analyzer for your projects, you also got commands over here, similar idea, which is called the ETF command. Doesn't matter. And then under that, you got lots of subclasses, as you have seen. One of them is simply called ETF, and then type check, just one of the commands, right? So now, if the user actually wants to do type check, what we will do is we're also going to actually create an instance of the relevant command. And then that one is going to call the relevant feature in the underlying model. Okay? One thing I want you to see, I will also show you some architecture diagram. So what is the direction of dependency? You can see that the UI, the user interface depends on the model. Okay, the UI depends on the model because you have to know which feature to call, like in these two cases, but not the other way around. So I'll just write it out explicitly. But the model doesn't depend on the UI. Okay, there's some direction of dependency you have to see. So what does that mean? That means, now let's say today, if I somehow try to use some particular patterns to implement the project analyzer, tomorrow I can choose to refactor my design, to change that to something that's completely different. In which case, whereas the user interface remain the same, for information hiding, all I got to do is simply just change the internal design over here. And then it's still going to work the same way from the external user's point of view. Okay? Again, just separation of concern. Okay? Now for your projects, I'll get there. I'll give you some connection by another diagram. I'll show that to you in a moment. Guys, any question about this overall picture here? It's nothing complicated. All I want to say is separation of concern. We got user interface, we also got model. The model is changeable to anything you want. Whenever you change the model, because of information hiding, it's not going to affect the user interface. The user interface is stable, always there. Okay, let's go back. Okay, so now we got events and features. Features or methods, if you like the Java term. Okay, so events are simply interaction, features are computation, right? Just programming concept, okay? You can just go over the rest, okay? Just want to tell you the terminology, so they're different. Okay, let's say in the case of the bank ATM, so now we want to say rather than committing to a particular concrete user interface, like the one you saw on slide number 1, the concrete bank ATM machine over there, we simply want to say, as far as the user interactions are concerned, what kind of interaction do they want to have with the system? In this case, we simply say the user may want to create a new account, or they may want to deposit, they may want to withdraw, or they may want to transfer. So these are so-called abstract user interface, in which case you can simply declare them and then just try to generate some abstract UI out of it, rather than committing to a particular concrete design. Okay, let's see. Okay, ETF in a nutshell, I will leave that to you. So I think all the points should make sense to you. The thing I want to show you is ETF is a different kind of test compared with what we have done so far. Okay, so now I want you to just write it explicitly for you. Let's try to compare. First of all, we got ETF, and then we got eSpec. Now think about how we run tests in these two different frameworks. Of course, for eSpec, you can think of it, it's also like a JUnits. And for this one, I'm not sure. You're gonna find out what's the equivalent in Java. If you find it out, let me know, okay? As far as I know, there might be nothing like that, okay? But let's see. So now let's talk about the eSpec first. So first of all, this is so-called unit testing, which means the thing you are testing are really like individual classes or features or methods, okay? So you got classes, you got features, or you can say methods. Okay, that's what you have. Now, what's really important to see, for eSpec, you must know about the details of the implementation. Okay? Let's say you want to test array container, somehow you want to test how the array has been changed, maybe the indices or whatever, right? So now in that case, implementation are exposed. Implementation is relevance. Okay? It's relevant. Okay? I will just highlight that. It's really important to see. Now, in the case of the ETF, you can see that the way, one more thing. How do you specify the test cases? You wrote it in some programming language, Eiffel in this case, or in JD's case, you write in Java. Let me also put it. Also, test cases written in a programming language. Okay? Okay, that's what we have done so far before the projects. Now, let's see how the ETF is different. Okay, let's try to compare. First of all, the kind of testing we talk about is not really called unit testing, it's called acceptance testing. Acceptance testing. Acceptance testing basically is from the customer's or client's point of view. If you're trying to deliver this particular system to me, should I accept it or reject it? So that's why it's called acceptance testing. So just from a client's point of view. So now that means when you are trying to develop the test cases for the acceptance test, it is not necessarily the case that the programmer write the test cases. The customer can also do that, right? So now I want you to refer to what we had for you. Remember we got at1.txt and also at2.txt. For those cases, if you look at the format of those cases, are they in Java? No. Are they in Eiffel? No. They're actually in a form that's actually understandable by any other people without any prior programming experience. For example, you will see that over there in the case of the bank, I'll just give you one example. You might say new, and then I would say Steve. And then I can say also deposit. And then I can say Steve with maybe $200, right? That's kind of the test case you can run. But you don't have to write it in a programming language. So that's a really critical difference. Okay, I'll write it down. So now that means test cases not written in a programming language. Okay? Now, and also another critical point, you can see that in the case of the JUnit or ESPEC unit testing over here, we say that the implementation is relevant. However, in the case of the ETF, when I try to test your program using different 81, 82, in fact, I got 50 different test cases. In that case, do I have to know how you implement your program? I don't need to know, because all I know is you follow the same user interface that's being generated by ETF, okay? So now over here, I can say the implementation and design is not relevant. Okay, so when I test your program, I simply know that when I test your program, I can write something like 81 or 82. I simply just by list of event being the trace, and then to see what should be the expected outcome. But I don't really need to test your code internally. Okay, so that's really a different kind of testing we're doing. Okay, which is also something you should learn. Okay, rather than just testing the implementation, but you want to test more about the interaction with the whole system. Okay, so that's really the two kinds of testing we try to show you in this course. Any questions about ETF versus ESPEC? Or more in general, we got acceptance test versus unit test. Okay? That's really the main message over here. Okay, let me go back over here. Okay, you can follow the rest. So now this one over here simply to summarize what you can do for this kind of acceptance testing. Okay? So now let me just use the iPad quickly and then show you some key points over there. Okay, the same diagram. Let's see how this can fit into your projects. First of all, what you were given were just the analyzer events.txt. That's what you were given. Okay, events.txt. That's what you were given. Remember, you run the ETF-new, right? That's what you did to generate this particular starting projects, right? That's a starting project you have. Okay, and then what's really hidden from this picture here is how you develop the model. So that will be shown in the architecture. Okay, and now this code skeleton here, you have to somehow eventually connect to your own design and implementation. Okay, then eventually it has to be done, or you have done that already, right? And then you can also develop as many use cases as possible. Again, since we are doing acceptance testing, every use case we have, they are not really specified in any particular programming language. So simply just follow whatever the monitor events we have in the beginning, right? Okay. Okay. That's, again, and that's really the critical parts that's going to make everything work. Business model, the critical part. That's something you got to implement. Okay, questions? Yes?
So the business model is the ETF model?
That's a good question. So by default, if you remember when you first saw the generator projects, what we had was, by default, we just have a class called ETF model. I will show you another diagram in just a moment to show you the architecture. By default, it's simply the model, ETF model class that we gave to you. But what you should do ultimately is to replace this class or replace this reference here by something that you develop. For example, static analyzer or whatever you have. Okay? That's what you should do eventually. Okay? But you can see that always we got the monitor events unchanged. They're always stable. They represent the way the user is going to interact with your system. Doesn't matter how you implement the business model. As long as it works, then we are okay. Okay? And now, how do I test your program? The only thing I know about your submitted project is you're going to follow exactly this monitor events, which means if I call type check, if I call evaluates, somehow it's going to internally call some features in your implementation. How you do it, I don't quite care, as long as it does the right thing. Okay? Okay, again, separation of concern, information hiding. Okay, this one here just show you 3 different parts. So I want to just show you very quickly. So you can see here, this is the abstract UI we talk about. And how do we do that in order to generate an ETF project? We do a event.txt file like this, right? And then once you generate a new project, you can actually run, the events one by one as each test case. This is just one example. Okay. Now one more diagram to show you the architecture. Okay. So this diagram is really important. Okay. Now also try to link to your projects. It should be very easily linked. I just want to use the example from the tutorial, the bank example. First of all, I want you to notice what are the critical cluster. So this one does not show the whole story. I just show you the critical part of the story. First of all, we have something over here called a model. So this is the model cluster. So this one here is completely up to you. Completely up to you. Completely up to you. And this one over here is the command. So this is the abstract UI. Abstract user interface, which is stable. Okay? So you can see that the only connection we have is every command has a reference to some class, some class in your model. It can be bank, it can be analyzer, it can be expression, it can be expression operation, whatever you like. Okay? It's completely up to you. Okay? There's no right or wrong answer. Now let's try to link again to your lab number 4. When you did your undo redo pattern, you can think of the same separation of concern over here. So in the command cluster over here, we got command move left, right, and etc. In the model cluster, we got the solitaire game, which you developed in lab number 2, right? So again, we are trying to practice this kind of model view controller pattern over here. Okay, now the most critical thing is you don't necessarily have to understand every detail in the ETF. You're not expected to. But the only thing you should know is this link over here. This link here. Eventually, you want to make a connection to there. Okay? I will give you a little bit a suggestion there. If you really are not so confident to replace that model, which by default is ETF model, right? I'll give you a little hints. What you can do is simply go to Eiffel Studio there, rename the ETF model class as whatever class name you have already. And then, so that means every reference that you make will link there. Okay? What do I mean? Okay? Let me illustrate it to you. Let's say over here, by default, you got something called ETF model by default. And then every command simply just refer there, right? I'm talking about default case. Now in your project, in case you haven't linked your model into your the rest of the ETF, what you can do is you can simply use the refactoring tool in Eiffel Studio. If you're not sure, you can come to me, I'll show you. You can rename that to whatever you like. For example, analyzer. And everything else will just work, I hope. Okay? That's a little bit hints to you. Okay, you can also follow that. That's exactly what I said. So every time when a user is making some request, so you're going to create some command objects. And the command object is going to call the relevant feature or methods in your model cluster, right? Depending on which team I'm considering, the call feature might be different. Okay? Okay, one more slide to show you. So this is a typical way of how you can do it. And this is, again, consistent with how you did for lab number 4. Now, let's say you got ETF deposit is a command class, okay? So now over here, I'm not supposed to do any implementation over here. I'm trying to call some implementation in my model cluster. So now, basically, we are making the assumption that model is now has the right type, right? It can be analyzer, it can be bank, it can be whatever. And then you're just going to do a serious check to see if somehow this condition is not satisfied, that means I cannot call the relevant feature. I need to set some error message, right? And then eventually I can simply do that. Okay? And the last line over here, you can see that the last line is already included for every command class. And this has something to do with event-driven design, which we talked previously. You can feel free to find the details, or you can talk to me. Otherwise, just leave it there. Don't change it. Okay? Don't leave it out. Okay, that's about what I want to say about ETF. Any questions? Yes?
Error checking,
Yeah.
you also do that in model.
If you know what, you can certainly make it work if you do it in the model cluster. However, it's not the right design, because the idea is we want to keep the model cluster clean in the sense that we got require and ensure. We don't have the defensive style of programming. We leave all the error checking in the user interface. Yeah. Okay, guys, any questions before I move on? Okay. Hopefully now it makes a little bit more sense to you since you have been seeing some parts of the ETF. Okay, don't forget the due date has been extended. It will be next Monday, noon. Okay, don't forget. And then I'll set up the Dropbox soon as well. Okay, if no questions, let's talk about a new topic. And this is going to be either the last topic or the second last topic for the course, possibly second last. The last topic would be maybe something very small. But this one here is going to be a little bit mathematical, okay, which we have to learn. Okay. You can also read the chapter 11 for the complete details in the textbook. Yes?
Just a quick question
Yes.
for our next lab test coming up.
Yeah.
Will this be on?
No, so you just check the preparation guide for your lab test 3. Well, of course, it wouldn't be reasonable to cover that, right? Since I'm only teaching this today. No. Just check the lab test guide, you will see. I will say a few words at the end, outside the recording. How about that? Okay, well, I will do that. How about lab test? Okay, now, let's talk about some logic over here. First of all, I want to clarify some terminology here. I'm going to talk about the assertion. We talk about assertion like a require, ensure, or invariance. That's the 3 kinds of assertion or contracts we talk about so far in the course. Now, whenever we talk about assertion, for the rest of the lecture over here, I'm going to refer to assertion being weak or assertion being strong. But what do I really mean by that? Let's clarify that first before I go on to some examples. The way for you to think about it is, every time when you are getting a predicate, for example, x larger than 3, so what do I really mean by x larger than 3? Of course, you can just evaluate to true or false. But one way to see it is, think about the assertion being a set of satisfying values. In this case, if I say x larger than 3, what will be the set? It will be 4, 5, 6, 7, and etc. Okay? So now, for example, you got x larger than 3. It corresponds to this set over here. Okay? And then let's get something that's very similar. Let's say x larger than 4. In this case, you can see that the 2 sets are very, very similar to each other, right? However, you can see that they are not identical. Okay? Apparently, you can see that the corresponding satisfying values over here for x larger than 4 is strictly smaller than the corresponding set for x larger than 3. Agree? Because you can see apparently the x larger than 4 set does not have 4. It does not, right? So it is strictly smaller. So now every time if I give you 2 predicates, if you somehow you can really see what's the corresponding set of satisfying values. Now, whichever that is has a smaller set, we say that the predicate is stronger. Okay? Let me just show you the definition and then give you some intuition. So now we say that an assertion P is stronger than another one. So it's relative. Okay? Assertion P is stronger than assertion Q if the corresponding set for P is strictly smaller than corresponding set for Q. In this, also logically speaking, we say P implies Q. Okay? Let me give you some example. For example, over here, I'm going to use the iPad. Let me just copy that and I'll show you this, this slide. Give me one moment. Okay. So now, let's see this. X larger than 4 implies X larger than 3. Okay? Let's see what this really means. Okay? Thinking this way. if I try to draw, this is a set of values for x larger than 3. Okay? If I want to draw the corresponding set for x larger than 4, how will I draw it? It should be completely contained inside this set, right? In that case, I can draw, I'll use a different color here. I can say over here, x is larger than 4. Okay, now, can you give me one value that is actually in here, but not here? 3 or 4? 4, right? Because remember, this is strictly larger than, right? So 4 larger than 3 is actually true, so it should be there. But 4 larger than 4 is false, so it's not there, right? For example, 4. Okay? Okay, now, you can see that x larger than 4, the corresponding set, is strictly smaller than x larger than 3 set. So now, what do we say? We say that x larger than 4 is stronger than x larger than 3. So give you some intuition. What does it really mean for predicate to be stronger? In this case, why do we say x larger than 4 is stronger than x larger than 3? If a predicate is stronger, that means it allows fewer values to be included in the set. Okay? I'll write it down. Stronger means allows fewer values to be included. To be included in the set. Okay? You can say the opposite as well. When I say x larger than 4 is stronger than x larger than 3, I can say the other way around. I'll write it down as well. You can say, put it here, x larger than 3 is weaker than x larger than 4. So what does weaker mean intuitively? Weaker means you can allow more values to be included in the set. Okay? So that's weak. So it does not really stop values to be included. Okay? That allows more values to be included. To be included. Okay? Stronger and weaker. The reason that I talk about these two notions first is because all our discussion for the rest of the lecture depends on this. Okay? So now you should know that logically speaking, if I can say one predicate implies the other, we say that the stronger one implies the weaker one. Okay? Just make sure you got the intuition here. Okay? Which means if you are in the stronger satisfying value set, you must be in the weaker satisfying value set as well. Okay? That's the intuition. Guys, any question about this? We'll see more examples in a moment. But just make sure you got stronger and weaker. We'll get there. Okay? Now, let's do some little bit practice over here. Given that we agree on the stronger versus weaker, or strong versus weak. Let's, what is the weakest assertion? Weakest. Why do you think weakest is the, why do you think true is the weakest assertion? Yeah, exactly, because it accepts everything, right? That's exactly right. The reason that, you can see that, by the way, in 1090 or 1019, I'm not sure which course, how do you describe a set that includes everything? It's called a universal set, right? In your 1019, just to draw some connection. So the weakest assertion there is true. And what about strongest? False for symmetry, but why? Why is false the strongest assertion? Say that again? It doesn't accept anything. So now, let me go a little bit further. What's the corresponding set of satisfying values for false? Nothing, empty set. Okay, good. Okay, hopefully that helps you understand. Okay, of course in reality, so now why do we learn this? Because precondition, postcondition, and clause invariance, they are all assertions. So now that's why we need a notion about whether your precondition or postcondition, well, especially precondition, is my precondition design has been too weak or too strong. I'll show you cases where things might go wrong if you got some precondition that's too weak or too strong. Okay, Now, let's bring the context back to decide by contracts, okay? So now we say that, first of all, when you talk about invariance, invariant is like there's acceptable states for your objects, okay? Let me just give you one example here. Let's say we got two possible invariants over here, okay? You have let's say account, okay? The class account. So now let's say we've got two possible invariant. Invariant number one, the balance of the account is larger than 0, okay? That means for an account object to be valid, the balance must be strictly positive. And the second invariant is the balance is larger than 100. Now, can you see which invariant is weaker? Which one is weaker? The first one? The first one, why? Because you can give me one example which would be allowed in the first invariant, but not in the second one. 10? Exactly, anything that's less than 100, right? Okay, because for example, if you say 10 larger than 0 is okay for the first invariant, so that object state is included in the set. But 10 larger than 100 for the second invariant will be false, so that's not included. Okay, just give you some feel. Because we always should talk about what should be the design for my invariance or for my precondition. Should it be too strong? Has that been designed to be too strong or too weak, right? So that's something we need to worry about. Okay, and similarly for weaker precondition, okay? And when we say a precondition is weaker than the other one, that means we are setting more input values compared with the stronger one. We'll see example in the next slide. And similarly, also for postcondition, that can be either weaker or stronger, okay? Guys, any questions before we see some example? Are we okay? Okay, let's see some example, simple one. Let's now consider this Eiffel program here, okay? So we have a class called foo, and then we got only one single attribute. Let's say there's no invariance, okay? But of course, if you want to bring the invariant into play, think of invariant being the postcondition for every feature, okay? But now let's say we don't have invariance. Only one attribute called I. Let's say we have a command called increment by 9, okay? We got a precondition, we got a implementation there, simply do the increments, and also we got a postcondition there, I larger than 13, okay? Can you see any issue for this particular there? Okay, I'll hold it a bit, okay? Anybody else before I try to let Doosan speak? Can you see any potential issue over here, as is? When I say, would there be any issue? And so if I try to somehow run this at the runtime, am I going to run into any violation? Would there be anything that will go wrong? Yes, go ahead.
Violation because if you enter 4 here and you split it by 9, it'll be 13, and you're in trouble with break.
Aha, exactly. So now, thinking this way, before I ask you further. So let's think about one case. Let's say the current value of I is simply 4, okay? And I'm trying to call the object dot increment by 9. So 4 larger than 3 is simply true. That means I can execute the body of the feature. In that case, I will be incremented from 4 into 13. But 13 does not satisfy the postcondition, right? So that means I run into the postcondition violation as is. So now, let me ask a little bit further. Let's say the implementation is apparently right because we are trying to say increment by 9. So just increment that. And then, question for you. Let's say we don't change the postcondition. Postcondition is what it is. Is the existing precondition too weak or too strong? Too weak? Think about what weak really means intuitively. If we say that the precondition there is too weak, that means it allows more input values than it should be allowing, right? In this case, what is that? 4, right? Because if you get 4, exactly what I said, it's too weak, okay? Okay, it's too weak. And then, because if it allows 4, but it should not be allowed, okay? Let me show you another one. How about this feature here? It's basically the same. I just changed the precondition a little bit. Do you think we'll run into any issue at the runtime? That means I can only try to call this feature here when I is larger than 5, meaning that it can be 6, can be 7, can be 8. Yes. Okay, very good. So the observation, there are two things over here. First of all, let's talk about if this might be any violation we might have as before. The answer is no, because the smallest value you can pass, you can call this feature is when I is 6, in which case 6 plus 9 would be 15. You are always guaranteed to satisfy the post condition. However, there's one concern over here, right? Because this precondition here, this allows a particular value which you may or may not want to include, which is 5, right? Because if I is actually happens to be 5, in that case, 5 plus 9 will still be 14, which is greater than 13, right? So now is I larger than 5 too weak or too strong? So the answer is maybe it's too strong, because whether or not you really want to disallow this value 5 is completely up to your application. If you really want 5 to be allowed, you allow it. Otherwise, you don't allow it. Okay, I'll get to some point. You will see why I want to show you two examples. One, it might be too strong. The previous one is too weak. Okay, how can we have a measure over there to say that if you try to make your precondition weaker than that, you're going to run into trouble. If you try to make your postcondition stronger than that, you're safe. Okay, that's kind of the thing we are trying to show you logically. You can only do this when you talk about logic. Okay, we'll get there. Guys, any question about what we have gone through so far? Are we okay? Okay, good. Okay, let's talk about a little bit about correctness. Remember in lecture number 1, I believe, I said that the correctness of your software is relative, which means you cannot say my software is absolutely correct, because it really depends on what you really want. And how do we make it clear what you really want? We have specification. And how do we write specification? We have contracts, precondition, postcondition, and class invariants. So that's why it's relative. So you want to make sure, when I say my software is correct, that means in a way my implementation in the do block is consistent with the required ensure and invariants. There's no violation at the runtime. Okay, that's relative notion. Okay, that means we need a specification. In the case of Eiffel, we do have required ensure and also all the contract for you. Okay. So now this one here, basically, let's try to read this together. Okay, we'll get there in more details. What we will do for the rest of the lecture today and also on Wednesday, we're going to show you a formal and systematic way of proving that your program is correct or not correct. Okay, so how do we do that? If I simply get something like this, for example, so this is a program over here, I cannot really try to manipulate this program to prove things directly. So what we have to do is to use a particular syntax, which is very easy to learn. And then we're going to use that syntax to prove if that syntax can be proved true. If it can be proved true, that means the original program is correct. Otherwise, it's not. Okay? Let me just show you one example here. Okay, let me just go to the iPad. Okay, let me just give you one example here. So first of all, we talk about program. Okay, so now program here, let me say I just got something similar to as before. Let's say increments by 9. Okay, over there we got require, and we got do, and we have ensure, and then end. Okay, so now let me use, first of all, we say that I is assigned to I plus 9. Okay, of course you got attributes. Okay, let me use different color to show you the precondition, postcondition, so you will see more obvious. Okay, I can say I is larger than, for example, 3. That's one case, right? And then over here I'm going to use red, but postcondition. Let's say I is larger than 13. As we learned from the previous example there, somehow we must be able to prove formally that this is not correct, this program here, because somehow the precondition is too weak, right? We allow also 4 to be included. Okay? So now, how do we prove it? So we're going to show you a very simple way to transform this program here into some special syntax. I'll tell you what the syntax means in just a moment, but let's just do that quickly. This is how you write a syntax. You got curly brackets here, curly brackets here, curly brackets here, curly brackets here. So now what do we put? Basically, let me just tell you what you should put. What you put in within the first pair of curly brackets is the precondition. In this case, I'll put I larger than 3. Okay? And then what I put within the second pair of curly brackets over here is a postcondition. And then, in this case, I larger than 13. Okay? And what do I put in the middle? Whatever that's within the do block. Okay? In this case, I will simply say, okay, over here, I is assigned to I plus 9. So somehow, you can see basically all the information is there. It's simply that once it's transformed, I don't have the require, ensure, and do anymore. I simply got some symbols over there, right? Later on, we're going to see that when you get anything like this, you want to show that whether I can prove that, okay, by the way, this is simply a predicates. Okay? I'll talk about what this predicate really means in just a moment. So this is a predicates, okay? Which can be proved either to be true or it cannot be proved to be true, either case, right? If can be proved true, so that means this program here is correct. Otherwise, it is not correct. Okay? Let's get this big picture clear first. Okay? You're given some program here with the precondition, postcondition, and whatever the implementation is. In this case, it's a simple assignment. It's easy to see. But as we will see later on today and also Wednesday, you may have, if then else, you may have sequential composition like a semicolon in Java. Also, you may have loops that will get things very complicated, right? But that's why this approach here is completely formal and systematic. That means you can always try to argue about the correctness of your program, okay? Given the pre and post conditions, okay? Okay, of course, let me just give you one more example here. In case I change this to be I larger than, what about 5 over here? In that case, I just need to put I larger than 5 over here instead, right? So I still got the same syntax over there. And then, in that case, I still want to prove it as true, or it cannot be proved as true. Okay. Guys, any questions before I move on? Yes? Correct. Yeah, so that means it's correct with respect to the current pre and post conditions. Yeah. So as I said, yeah, I'll give you a question. As I said before, the notion about correctness is relative, okay? That means my implementation is correct with respect to its current pre and post conditions. Okay. Questions?
Predicate can violate true, but the condition.
Oh, we'll get there. Yeah. So somehow you will see that the precondition, post-condition here, they're simply just they're also just Boolean conditions. In the extreme cases, the precondition might just be true, or it can be false. And the post-condition here can also be true or false, right? We'll get to those cases. Okay. I'll get there. Okay. Okay, let's go on. Okay, let's say, for example, over here, so this is one possible predicate here. You got the precondition there, the body of the implementation, and postcondition, right? And somehow, okay, and then we just got another example, right? Just with a different precondition. Okay, so these are two possible predicates you can generate from your program. Now, somehow we want to say if the predicate we have can be proved to be true, that means the original program that we translate the predicate from is correct. For example, I will show you that we can prove that this particular predicate can be proved as true, right? Because I larger than 5, even though it's a little bit stronger than necessary, maybe, but it's correct because we cannot have any violation at the runtime, right? So what we just talked about in the previous slide was just intuition, but we try to give you more formal account. On the other hand, this predicate here, where the precondition is I larger than 3, in that case, we'll show you that you simply just cannot prove that this predicate is true. In that case, we can conclude the program that you translate this into is not correct. Okay? So the kind of question you can expect, not in the lab test, but in the exam, I might give you some simple fragment of code with precondition and postcondition, and the implementation may have loops, may have if then else, may have assignments, like a combination of all. And then I want you to argue to me if the program is correct or not. So step number 1, translate the program into this kind of syntax here. And then try to follow the rules I'm going to show you now so you can prove it. Okay? Of course, for the final exam, I'm going to allow some data sheets for you so you can put whatever thing you like on the sheets. Okay? I'll talk more about that maybe next Monday. Okay, now this is the formalism that we're going to learn in order to prove some correctness of simple program. So proving program correctness is a very big research area. So people have been trying to prove the correctness of C programs by keeping track of the pointers, or they try to prove the object-oriented program like Java. So people have been trying to do that in the research area. But all of them have some foundation called a Hoare logic, more or less. Okay, we'll only learn the introduction to it just for you to get some flavor. If you want further references, let me know. I can give you some papers to read outside this course. Okay, let's now say a little bit more general. Let's say for any program with implementation S and also precondition Q and postcondition R. I'm going to follow this kind of color convention here. Whenever you see green, that means precondition, okay, and Q. And also red will be postcondition. That's more or less the convention I'm going to follow. Okay, so now let's try to understand what this really means, and I'll give you an example. Okay? So when I have two pairs of curly brackets over here, I got precondition first, I got postcondition, and in between I got the program S over there. And then we say that it's a correctness predicate of the program S. So that means given S, Q, and R, I can write out this predicate here. And then we're going to follow certain rule to prove this predicate being true. If we can manage to do that, that means the original program S is simply correct. Otherwise, it's not correct. Okay? That's why it's called correctness predicate. And then let's try to see what this what the syntax here really means. Okay? Let's try to go over that. The idea is simple. It's pretty much like how you understand how the Eiffel program is executed. Starting from, so under what circumstances can we execute S? Is when the precondition Q is true. And we also say that once the execution of S is done, we have to make sure the postcondition R is established exactly the same. Okay? So there should be no surprise here. Let's just go over that. So we say that this correctness predicate here is true, which means we can prove that to be true if the program S, which can be arbitrarily complicated, it starts executing in a state satisfying the precondition Q. Okay, first of all, and then there would be two concerns over here. So far, I have seen some submissions for the lab and also for the lab test, in which case the submission simply did not terminate on my test cases. Right? So in that case, it's not very good because you want to make sure termination should be a property of your program. Okay? Because we talk about if it doesn't terminate, you never know what the outcome should be. Okay? So we talk about termination as well. Usually, you don't have to worry about termination if your program only contains sequential composition, semicolon, assignments, or if then else. But as soon as you introduce the notion about loops, in that case, you got to worry about termination. So that's something I will talk about in details on Wednesday and possibly part of Monday. I think that'll be something very important for you to take away. Okay, now, first of all, we say that the program will be correct. First of all, the program itself terminates, right? And the second thing is, given that the program terminates, we want to make sure it terminates in a state that satisfies the postcondition. So you can see that there are two concerns over here. Again, separation of concerns. So we don't try to prove about termination and the establishment of postcondition at the same time. We do that in A and B separately. Okay? So A is about if the program terminates, and B is about given that it terminates, assume that it terminates, then we want to make sure it satisfies the postcondition R. Okay, so there are two aspects you want to see. Okay, good. Now let's talk about some terminology here. So A here, termination, and now for B here, you can see for B here, we simply assume the program is going to terminate. We say, assuming that it terminates, now let's see what's going to be the terminating states. Okay? That's why I call it partial correctness. If you can prove B, that's only partial correctness because you got to also prove A about termination. And then with A and B together, you can say it's total correctness. Okay? So hopefully the words about partial and total make sense to you, right? Partial means you haven't proved about termination. When you say total, that means you have proved two things. First of all, your program terminates, and also second, given that it terminates, it's going to establish the postcondition. So two things. Guys, questions? Again, definition first, before I show you examples. Questions? Okay, let's see. Let's go on. Before I show you how you can do systematic calculation for this predicate here, before I do that, let's just go over one more slide. Let's try to link a little bit more intuitively to your contracts. You know, oh, by the way, we call this the Hoare Triple. I'll write it down. So whenever you have this precondition Q, program S, postcondition R, we call that a Hoare Triple. So Tony Hoare is, again, the inventor for the quicksort. And remember, we talked about this name when we talk about void safety, right? About a null pointer, okay? Just, again, the same person. Anyway, so that's a triple. You don't have to know, you don't have to memorize the name, okay? I'm just saying it's good to know. Triple because we got three pieces of information here, okay? That's why. Okay, let's just go over a little bit more intuition. Okay, again, Q is the precondition, S is the implementation, which can be arbitrarily complicated, and R is the postcondition. Okay. Now, let's just go over some different extreme cases to get some feel. Okay. Now, let's consider this. What kind of situation are we dealing with over here? You can see that S is anything, R is also anything. The only thing that's definite is the green part. And what's the green part? The precondition, right? So what does it really mean when the precondition is simply just true? Nothing? It means something, not nothing. Always pass. From the client's point of view, right? The client should be very happy because it does not impose any constraint on the input. I can always call the feature. It's guaranteed to be accepted. Okay? That's one extreme. So that means all the inputs are valid, so that's the most friendly feature you can implement, which means you assume nothing on the inputs. Whatever the client passed to you, you just do it. Okay? What about this one here? Nothing is accepted. So do you think this will be useful at all? No, right? Because now it doesn't matter what the client passed as input, you always reject. So they can never use your feature over here, right? So that means that's the most useless feature, okay? How about this one here? What does this one mean? Any precondition there, but now the only thing that's definite is the postcondition is true. What does that mean here? Do you think, okay, let's say I'm giving this job to you as a programmer. How about that? Do you think you'll be very happy, or you think that's too challenging?
It will say that any value produced by the program should be correct output, which means
any output will be accepted, right? Any output will be considered as valid. In that case, you as an implementer, you should be very happy if this is a job offered to you, because whatever you produced, the postcondition is going to be true, right? So now this is going to be really easy for the programmer, but very risky for the clients, right? Because whatever they try to call, they simply don't know what's going to be done because the postcondition is simply true. Okay? How about this one here? Wow, this one, do you think you'll be very happy to get this job here as an implementer? False. Yeah, you get the pickiest clients ever for no reason. They simply say no, 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 right? Okay, so now the post condition being false, that means any output value will be just invalid. Doesn't matter what they are. In that case, that'll be the most challenging task for you to do. Okay, now what's this? Think about this case. This I'm trying to lead towards this case over here. What's this case? When I say the precondition is true and the post condition is true, what is that? Huh? Accept everything, and then everything produced can be okay. It's actually not very informative, right? So now, think of this as the case where you're not trying to make use of the side by contract that we teach you. Let's say one day, you try to write your maybe whatever C function, Java methods, or C# or C++. Somehow you really don't have a sense about what a precondition should be. Anything's okay, maybe. And also you don't have any notion about what a post condition should be. So now in this case, you simply have no idea what you're doing. Well, I'm trying to exaggerate a little bit. Of course you know what you're doing. I'm just trying to say, for large scale projects, it's not very good style to simply say anything's okay as inputs, anything is also okay for the output. That's not very informative, right? You really want the contract view of your feature or your methods to show you some contract, right? Some informative contracts. Okay, now let's get to Hoare logic very quickly. Okay, I believe this slide here is simply just repetition. Okay, you can just go over them. Okay. Okay, now just one thing I want to show you. Let's say this. If I have a program like this, I got n is assigned to n plus 9, or I is assigned to I plus 9. And the post condition is n larger than 13. Okay. Now, let me just rephrase our discussion a little bit from before. Now, let's say I want to design a precondition such that if the input passed the precondition, and then I try to execute the code, it's guaranteed the post condition is gonna be satisfied. Now, what should the question mark, what should that be? In this case, it's easy to see it's n greater than 4 in this case. But how do we know, right? There's got to be a way to systematically calculate this. So that's why we had to learn about something called weakest precondition calculus. Okay, do some questions.
Is it where we take the 13 and minus the 9, because it's added to the...
Something like that. Something like that. You will see that, yeah. In this simple case here, you can see we only got assignments in the program. In that case, it satisfies a particular rule. But when you get things that's more complicated, you got loops, you got if then else, things will get more complicated. We'll get there. Okay. Okay, so now the concern is, given the post condition, which can be invariant for your class, and also given the implementation we want to do, what should be the corresponding precondition that will be safe, that will make our program correct? So that's the question we're asking. Okay, so now, this is one notion I want to introduce first, and then we'll see how to do it. Now, in this case, as some of you actually observed, it should be n larger than 4. So we say that this precondition here is the weakest, WP. Okay, you should really know this acronym here, WP, weakest precondition. So what does weakest precondition mean? So let's think about what the n larger than 4 is. We say that n larger than 4 is the weakest precondition for n is assigned to n plus 9 to establish the post condition n larger than 13. It's the weakest one, which means if you try to give anything that's weaker, you're going to run into trouble. Let's try something weaker. N larger than 3. N larger than 3 is weaker than n larger than 4, as we learned before from the previous slide. In that case, because somehow I will show you how to calculate the weakest one. Once you have the weakest precondition there, you can design your precondition to be anything that's either equal to it or stronger than that. Then you'll be safe. If you try anything that's weaker, then you run into trouble. That's an intuition. Okay? Weakest precondition. Okay. Okay. Now, okay, any precondition that's equal to or stronger than that, it will be a correct program, right? For example, n larger than 5. N larger than 5 is actually stronger than that, so we are fine. Okay? And also, anything that's weaker than the weakest precondition, which we'll show you in the next slide how to calculate that, and it's going to be an incorrect program. In this case, for example, n larger than 3 is actually weaker than that, right? So it's not good. And you can always give a counterexample. Okay? So guys, this slide here, mainly the thing I want to mention is about the weakest precondition. Okay? And then now the question is, how do we calculate the weakest precondition systematically? Okay? Now this is now the focus. Okay? So for today, we'll try to do a few, and then we'll try to do the rest, possibly on Wednesday and next Monday. I want to go slowly. Otherwise, I don't want you to get too rushed on this subject here. I'll give you some exercises to prepare for the final next week. Okay, so now, let's have some idea over here. So now, given that we have a Hoare triple here, we got a precondition Q, postcondition R, and program S. So what do we mean when we want to prove that this predicate here is true? Okay, so that means the following. We want to say whatever precondition we have implies the WP. Okay, let me just write it down. Okay, how to prove? Thank you. Can you see that? Okay, yeah. Sorry. How to prove? Let's say we got Hoare triple here, Q over here, program S, okay, and then postcondition R. How do we prove that this is true? First of all, we want, when we, let me just break it down into two parts for you. This is the first part. So you have the program, you have the postcondition, from which, step number one, calculate the weakest precondition for program S to establish R. Postcondition R. And let's write it like this, and now I'm going to show you how you can do that. So WP over here, given some program S, and then I want to establish R. So this is going to give me another predicate, which is the weakest precondition. Okay? Now, the second part is, I want to know if my current precondition Q is appropriate or not. So what does it really mean for that to be appropriate? That means it is no weaker than the weakest precondition. Okay? Now, I want to prove that Q is no weaker than WP for S to establish R. So what do I mean? I mean Q implies, which means it's stronger, right? It's either equal to or stronger, the WP for S and R. So this is the most important slide to get clear the big picture. Okay, so I will show you exactly how you can calculate this in just a moment. Okay, and now let's get it clear. How complicated can S be? Right? What can S be? Well, it can be, first of all, it can be assignments. X is assigned to some expression E. That's one way. Or it can be, if then else, I can say if some Boolean condition, and then I'm going to do some program statements S1. Otherwise, I'll do something else S2. Right? That's alternation we call it. And also, we got sequential composition. Okay? So that means I got S1 followed by S2. Okay? And number 4, I'll just put loops over here. We'll get to loops. That's more complicated than all the others. So now this is how complicated S can be, and R is simply just an assertion. Okay? Once we calculate WP, the next step, step number 2, we want to make sure the precondition we have is no weaker than the weakest precondition we calculate. Okay? So these are the 2 steps. Okay, now think back to the very first example we did. Okay? Let me just give you some idea, and then I'll come back to this slide in just a moment. Okay? Now just go back here and go to our very first example over there. I want to just summarize the steps, and then I'll go to WP calculation. Now, go back to this original question here. Is this Eiffel program correct or not? Okay? What you should do is, first of all, step number 1, you want to translate this into the Hoare triple, right? With the precondition, program S, and postcondition, step number 1. Step number 2, you want to calculate what's the weakest precondition for I is assigned to I plus 9 to establish I larger than 13. Okay? That's the second step. And once you get a weakest precondition from step number 2, let's go to the final step. The existing precondition is I larger than 5 does that logically imply the weakest precondition you just calculated in step number 2? If you can show that it is the case, then the program is correct. If you cannot show that, i.e. you can give some counterexample where it does not hold in general. In that case, the program would not be correct. Okay. Guys, any questions until now? Just conceptually. So you can see that yes. Oh yeah, exactly. So good question there. So now I'm going to give you, I'll review the example to begin with maybe on Wednesday. Okay. Basically for this example here, for this particular program, by following the 3 steps, you're going to see that we just cannot prove the corresponding Hoare triple is, actually, we can actually do that actually. We can prove that it's true. Okay. But in the other example, we cannot. Okay. We'll get there. Okay. Okay guys, let's go over some rules. Okay. Okay, let's now see how we can calculate. Okay, so the Program-S can be assignments, it can be alternations, if and else, conditionals. Sequential compositions, in Eiffel, you simply don't necessarily have the semicolon. You can imagine that we got semicolon, okay? Just like in Java. And then we got loops. So I'll come to loops on Wednesday, maybe the second half on Wednesday. And now, let's see how we can do the weakest precondition calculation. Let's now do it in this order. I'm gonna show you assignments, alternation, sequential composition, and then I'll do loops. Okay, let's see how much we can do today. Okay, and then we'll do exercises as well. Okay, just one more slide to show you over here. So sometimes when you do the proof, you may want to distinguish between the pre-state value and the post-state value. The way we do this for the post-condition in Eiffel is by saying old keyword, right? But now to really save, to make it a little bit more concise, the way we do this is by using this. So in the post-condition there, you can either say pre-states, you used to say old x, but now we simply say x with the subscript 0. Okay? That means it's the value before the feature or command was executed. Okay? And also we can use simply x, just like in Eiffel. Okay? That means it's after the feature is executed. Okay? You will see how we can use it. Okay, you can go over the rest. So I'll go over these 2 points maybe when we get to the rule. Okay? Okay, now this is the first rule. Let me give you some idea the flow. Okay? How do we define WP? WP. Okay? This is general form. WP, you're gonna take some program statements. Program, just some code. And then that's the first argument. The second argument is going to be some assertion. Okay, so now we're going to introduce different things. Okay, let me just give you a preview. So we're going to say WP, and then if I say X is assigned to some expression E, and whatever R I have, what should be the weakest precondition? Okay, and then I would say I got WP over here, and then I simply say if some Boolean condition here, I'm going to do sum S1. Otherwise, I will do S2. Okay. And N. So this is the programming part. And then any post condition here, and that's going to be what? Okay. Again, I'm going to say another weakest precondition here, S1 followed by S2, which means execute S1 and then execute S2. Okay, and then here we got post condition here. And that's going to be what as well. Okay, over here I just want to highlight. So this is one kind of programming statements. That's the second kind, the third kind. Okay, we can consider one by one. And also the fourth kind will just be loop. I will do that later. You will see that all of these are actually straightforward. It's just that we are trying to make it formal. Okay, let's go over them very quickly. Let's go over the first one. The first one is the easiest. So what does it mean when I say if my implementation is to actually do an assignment over here, and I want to say after the assignment, I want to establish this post condition. So what should be the corresponding weakest precondition, right? Okay, let's go there. Now, that's exactly this. So now, this is what it should be systematically. That means, let me explain to you what this means. That means whatever postcondition you have, you're going to replace every occurrence of the value that's being assigned to by its new value, which is the expression. Okay? So now, so you can read it, but let's just see an example here. So now over here, let's say we have a program. X is assigned to x plus 1. Okay? And let's say we got a postcondition here. X is larger than x0, which means old x. Okay? Now, what should be the corresponding weakest precondition? Okay? Let's see how we can calculate. Okay? Let's see this example here. So now that means what kind of precondition we put it here? Anything that's equal to or stronger than the weakest precondition would be okay. But now, what's the weakest precondition then? Let's calculate that. Okay? Okay, so now, if you want to prove that, you're going to say that whatever precondition you have must imply the weakest precondition of this, right? But now the thing is, how do we calculate this? Okay, let me just illustrate this, and then we'll be done. Okay, let's just do this example here, and then we'll continue from the rest. I'll write it down on the iPad first, and then I'll show you. Yeah, I know, it's intentional. I'm just writing that down. Okay, now let's see that. Okay, guys, let's just do this one very quickly. It's very easy to do. So now, this one here, how do we calculate the weakest precondition? Thinking this way, this is the postcondition we want to establish over here. We are saying that the post-state value, which is x, must be larger than the pre-state value. Which means we are doing something that's going to make x bigger, right? So now, what we can do is, let me just, according to the rule, copy down the postcondition. X larger than x0 over here. And then I'm going to replace, because I know that this is the value I'm trying to change, right? Not x0. x0 is always there, right? The pre-state value. I'm going to say x is going to be replaced by x0 plus 1 in this case, because you can think of conceptually, the x over here is simply x0, right? So now, what will be that replacement? I'm going to replace x by x0 plus 1. x0 plus 1 larger than x0. Are you okay with this substitution over here? Okay, so because I know that I'm trying to assign x to be x plus 1, so that means the way to do it is by replacing every occurrence of x by x0 plus 1. So now, what would this simplify into? Would that be something that's always true or not necessarily? Well, if you try that, you can see that if I try to get rid of this both sides, I got 1 larger than 0, which is always true. So what does that mean? That means the weakest precondition for this implementation here to establish that is always true. Which means it doesn't matter how you constrain the inputs, as long as you execute the program, it's always going to establish the postcondition. Okay? So now, when you go back to the slide, that's exactly show you the step over here. By Wednesday, go over until this slide here, and then we'll continue for the rest. And let me stop the recording here.